Hello everyone and welcome back to Math Made Easy. I hope you have been following the numerical analysis series from the very beginning because today's lecture builds upon everything we have learned so far. So let's just quickly recall our journey. So we started by understanding what numerical analysis is and why numerical methods are needed to solve mathematical problems that can't be solved exactly. Then we discussed different types of error that arises during numerical computations and learn how to measure and control them. And after that, we moved to the problem of finding the roots of the nonlinear equation. And to solve these type of problem, we first studied the intermediate value theorem, which guarantees the existence of a root under suitable conditions. And using that theorem, we learned the bisection method, one of the most simplest and most reliable bracketing method. Then we improved upon it by studying the regular falsy method, where instead of taking the midpoint, we use the x-intercept of the second line joining the endpoints. And in the previous lecture, we studied the Newton-Raphson method, one of the fastest numerical methods. We saw that instead of using a second line, Newton-Raphson uses the tangent to the curve to obtain the next approximation. And the Newton-Raphson method converges very rapidly and is widely used in engineering as well as the scientific computations. However, it has one major limitation. It requires the computation of the derivative of the function. Now, imagine that you are dealing with a complicated function obtained from experimental data or computer simulation. Sometimes the derivative is difficult to evaluate, and in some situations it may not be even available. And it naturally raises an important question. Can we obtain a method that is almost as efficient as Newton-Raphson method but doesn't require the differentiation? And the answer is obviously yes. Today's lecture is devoted to one of the most elegant methods in numerical analysis, the secant method. Now let's just understand why the secant method is needed. Recall that Newton-Raphson iteration formula. So we have this xn plus 1 equals to xn minus f of xn divided by f dash xn. Now observe this equation carefully. Everything in this formula is easy to compute except one quantity, that is this f dash xn. And to apply the Newton-Raphson method, we must know the derivative of the function. For simpler polynomial type of function, this is straightforward. But consider functions like this x square plus log x minus sin x square plus e to the power x square into log x. Now, differentiating such functions repeatedly may become tedious, and in many practical engineering problems, the function is not even available in analytical form. Instead, we may only know its values at different points, and in such situations, Newton-Raphson can't be applied conveniently. So the question becomes, can we estimate the derivative instead of calculating it exactly? So the secant method answers this question. Instead of calculating the slope of the tangent, we calculate the slope of the secant line. And that small change eliminates the differentiation completely. Now let's just understand what the word secant means. And most of you have heard this term obviously in geometry. So basically the secant line is a straight line that intersects a curve at two distinct points. So if I draw a very smooth non-linear curve and mark 2 points as this Pn and Pn minus 1. Now join them by a straight line, and this straight line is obviously known as the secant line. Unlike the tangent, which touches the curve at only one point, a secant intersects the curve at 2 points, and these 2 points are these. So the slope of the secant line can be calculated very easily. We have the slope as this fxn minus f of xn minus 1 divided by xn minus 1. Now look carefully at this expression. Does it remind you of something? Exactly. And this is nothing but the finite difference approximation of the derivative. Therefore, instead of computing that f dash xn, we approximate it by this fxn minus f of xn minus 1 divided by xn minus 1. And this single approximation gives birth to the secant method. Now, here what we did, is just this. We have supposed we have two initial approximation as x0 and x1, and these two values are selected near the expected root. Now I just notice something important, like unlike the bisection method, I don't have to satisfy that fx0 and fx1 should be lesser than 0. The second method is an open method. It doesn't require any bracketing methods. Now considering the two corresponding points of the curve as this P0 and P1, now join these points by a second line and extend this line until it cuts the x-axis, and the x-coordinate of this intersection becomes our next approximation as x2. Now discard the oldest point and keep the latest two approximation and just repeat the process. Use that p1, p2 and to obtain the p3, and the process continues until successive approximation becomes sufficiently close. And this is why the second method is sometimes called as two-point iterative method. Now, are these 2 points chosen randomly? The answer is clearly no. Only the first two approximations are selected by us, and these are called as initial guesses. And after that, every new approximation is generated automatically by the iteration formula. So only x0 and x1 are user defined, and all the remaining values are computed by the algorithm itself. Now we come to the most important part of the today's lecture. Most of the students simply memorize the second method formula, and instead let us just derive it. We begin with the Newton-Raphson method, that is this xn plus 1 equals to xn minus fxn divided by f dash xn, marked it as the first equation. Now most of the student ask, like, what is the only quantity that causes difficulty? Now the question arises here, like, what is the only quantity that causes the difficulty? Exactly this f dash xn. So instead of computing the derivative, replace it by the slope of the second line. That is this can be approximated by this f dash xn. So you need to substitute this approximation into a Newton-Raphson method now. So you get this xn plus 1 equals to xn minus this f of xn divided by f of xn minus f of xn minus 1 divided by xn minus 1. Now simplify just this complex fraction. Multiplying by the reciprocal, we successfully obtain this xn plus 1 equals to xn minus fxn multiplied by xn minus 1 divided by this f of xn minus f of xn minus 1. And finally, we got this answer. And this is the second method iteration formula. You are not expected to memorize it blindly. If you remember the Newton-Raphson method and the finite difference approximation of the derivative, you can derive the formula whenever required. And that makes the method much easier to understand and remember. Now that we have derived the second method formula, let us just understand the step-by-step algorithm as well. Whenever you solve a problem in an examination or implement the method in a computer program, these are the following exact step you should follow. Just have to given the equation in a very standard form, that is this fx equals to 0. Since every numerical root finding method starts with expressing the equation in the form fx equals to 0, and this makes the notation uniform and simplifies further calculations. Now you need to choose the two initial approximations as x0 and x1, and basically these are your starting values only. Unlike the bisection method and regular falsy method, there is no need to define the fx0 into fx1 is lesser than 0. However, the two values should be reasonably close to the expected root, but a poor choice may lead to slower convergence or even divergence. Now you need to evaluate the value for the function at this point x0 and the point x1. And these value will be substituted in the iteration formula, that is this second formula. And this gives us the next approximation. Now notice that the oldest approximation is discarded here. The newest approximation becomes part of the next second, and this is why the second method always works with the latest two approximation. Now you just need to repeat the iteration until one of the stopping criteria is satisfied. Now comes the question that asks for the positive root of this particular equation using the second method up to 4 decimal places. That is correct, up to 4 decimal places. So here we have this function as it is x square plus log x minus sin x minus 2 equals to 0. So firstly, we have defined the equation in the very standard form, that is this fx equals to this. Now let's just determine a suitable interval as well. So evaluating the function at x equals to 1, that means this is giving you f1 value as is minus 1.84147. And at x equals to 2, this f2 value becomes 1.78385. Now we get this f1 into f2 is lesser than this 0. That means this root always lies between 1 and 2. Although the second method doesn't require this bracketing, but these values provide good initial approximation. So we can take this x0 as 1 and x1 as 2. Now you have the second formula that we have discussed earlier. Now I just need to substitute the values for x0, x1 and their function values in the formula. And by that you get this x2 value as 1.50794. And the function value comes out as to be minus 0.31343. And with the second iteration, you can use your x1 as 2 now, discarding the x0 and taken this x2 as 1.50794. And substituting into the second formula, we get this x3 as 1.58152. And the function value will come out to be minus 0.01718. And with the third iteration, we get the x4 value as 1.58578 by using the x2 and x3 as 1.50794 and this 1.58152. And the function value comes out to be 0.00052. And lastly, with the fourth iteration, we get this x5 value as 1.58565. And the function value comes out to be minus 0.00001. And the required accuracy is hence being achieved. Looking into this iteration table, where we are having this xn plus values at the fourth and fifth iteration are identical, and hence we can get the positive root of this particular equation correct up to 4 decimal places, which comes out to be as 1.5857. And now you can notice that throughout the solution, we never differentiated the function. If we have used the Newton-Raphson method, we would first have to needed to compute the f dash x value. That is 2x plus 1 by x minus cos x. But the second method avoids this differentiation by approximating the derivative using the slope of the second line. And this makes it particularly useful when the derivative is difficult or expensive to evaluate. So today we explored the second method, one of the most important derivative-free techniques for solving nonlinear equations. We began by understanding the motivation behind the method and learned why it was developed as an alternative to the Newton-Raphson method, and we then started its geometrical interpretations, derived the second method formula using the finite difference approximation of the derivative, and discussed the complete algorithm stepwise. And finally, we applied the method to solve a university level numerical example and observed how successive approximation converged toward the required root without evaluating any derivatives. And one important point to remember is that the second point is an open method. It doesn't require that initial approximation to bracket the root. And unlike the Newton-Raphson method, it completely eliminates the need to compute the derivatives. And this actually makes it an efficient choice for many practical engineering and scientific problems, where derivative evaluation is difficult or computationally expensive. So in the next lecture, we will study another important iterative technique, the fixed point iteration method. We'll learn how to transform a nonlinear equation into the form of x equals to gx, some gx function, and understand the concept of a fixed point, derive its iteration formula, and most importantly, discuss the convergence criteria that determines whether the iteration approaches the required solution or diverge. Thank you for watching, and if you found this lecture helpful, please like the video and share it with your classmates, and subscribe to Math Made Easy to continue learning numerical analysis through clear explanation, detailed derivations, and solve examples. Until then, keep learning, keep practice, and keep questioning, and I'll see you in the next lecture.